The fourth case you would prove is when x is less than 0, y is greater than or equal to 0. However, you notice it's absent from the proof, and the reason why it's absent from the proof is if you have a look at the original result, it's symmetrical in x and y. You can switch x and y and the result still stays the same. And here, between case 3 and case 4, we've essentially switched x and y. And when you've got this sort of symmetry, when you switch two variables and it's still the same, you're just going to be repeating the same thing, just switching x and y, so it's pretty pointless. So what we do is we write the phrase without loss of generality. So what this is a way to reduce the cases when there is symmetry. Okay. So without loss of generality means we could prove a similar result which swapped x and y in the same way. Okay. It's just a way for us to reduce cases, reduce the amount of writing. Okay. So an interesting thing to look up there, and an interesting thing that is used in proof when there is symmetry to reduce the amount of cases we're looking at. Okay, let's push on. I wanted to do some further AMGM questions. Let's just jump straight in to these and we'll see if we can cover them all before the end of the period. We'll see how we go. So this is the first one. Now, notice one thing I noticed is I always like to look on the right hand side here to kind of work out what's going on here. If I brought that x under the square root, we'd have a square root of x squared y squared plus z squared. And I think that gives us a big hint of how to proceed in terms of the AMGM. I think we should set a to be x squared and b to be the second factor, so y squared plus z squared. So let's do that. We'll get x squared plus y squared plus z squared over 2 greater than or equal to root x squared and then bracket the y squared plus z squared, the product, which of course we can times by 2, and we can take that x, the root x squared out to just be an x. Okay. So we get that x squared plus y squared plus z squared is equal to this. I might keep I'll keep the 2 there. So that's one result, and the second result, hopefully you can see they've set a to be y squared if you bring that y under the root, and the b to be x squared plus z squared, and you'd get the same sort of result. You get y squared plus x squared plus z squared onto greater than or equal to root, that'll be y squared x squared plus z squared. Okay, which will rearrange to y squared. Well, the order doesn't matter, so x squared plus y squared plus z squared to be greater than or equal to 2, and then we'd have the y out the front, root x squared plus z squared. Okay, and then you can see that the right hand side of the result that we're trying to prove is just the addition of the 2. Okay, so if this is, call this one equation 1 and call this one equation 2, we do 1 plus 2. We'd have x squared plus y squared plus z squared plus another x squared plus y squared plus z squared being greater than or equal to 2 lots of x root y squared plus z squared plus 2 lots of y root x squared plus z squared. And then hopefully you can see you got 2 x squareds, 2 y squareds, 2 z squareds. You could take out a 2 there. And on the other side we can take out a 2 and we've got our result. Okay, for time's sake I'm not going to rewrite the final line, but you would in the exam. Okay, we're going to push on. We didn't do the AMGM proof of 4 variables, so I wanted to quickly do that. So it starts off with your basic AMGM for 2 variables, and what you do is you substitute something in here to try and prove this result. I like to go, for 4 variables, I like to go straight away the full shebang, and in order to get this left hand side, hopefully you can see that the left hand side is the same as a plus b on 2 plus c plus d on 2 all over 2. So I'm doing the AMGM, but instead of a I'm putting a plus b on 2, and instead of b I'm putting c plus d on 2. Okay, so that'll be greater than or equal to, using the AMGM, the square root of a plus b on 2 multiplied by c plus d on 2. And then what we do is we use the AMGM again. It's an AMGM within an AMGM. Okay, so I'm using this result here, and I'm using this result here. That'll be greater than or equal to root of root the product AB and root the product CD, which is the same as the square root of the square root of ABCD, which is the same as being the fourth root of ABCD. Okay, and the left hand side, at some stage you can write it as over 4. So it's the left hand side is what we want as required. Okay, so that's part A done. Part B, hence prove this result here. So hence meaning we need to use the part A result. The 4 on the right hand side will probably come from this 4 here. So I'm using the AMGM. I'm just going to simply write down exactly what we've got there. So the first bit's going to be A over B, the next bit's going to be B over C, the next bit's going to be C over D, the next bit's going to be D over A. All divided by 4 because there's 4 things, greater than or equal to the fourth root of the product. And what's nice is that you'll see this product, the product of all these ends up being 1. Things cancel. So A over B, B over C, C over D, and D over A. D's cancel, C's cancel, B's cancel, A's cancel. This is the fourth root of 1, which is just 1. Okay, multiply by 4, take the fourth root of 1, and that just becomes 4. And the left-hand side is what we want, okay? As required. Okay, I'm rushing because I know I'm running out of time. So a lot of the time when you've got fractions and then there's no root on the other side, consider what would happen if you multiply the fractions. Does everything cancel out nicely? And in this case it did. Okay, let's push on. So here we go. We've got AMGM. Okay, I've got three terms, 3 variables, and usually that's when you get the 3 pairs and you add, expecting it to be that. So let's just focus. Maybe we'll try 1 pair and see what we get. So AMGM with that 1 pair. Okay, so it'll be over 2, greater than or equal to the square root of the product of the top bits. So xy over z times by yz over x. And what you'll see is there's some cancellation here. Z cancels and x cancels, and we get square root of y squared. I'll times by 2. So I've got xy over z plus yz over x. It's greater than or equal to 2 root y squared. Well, that's just going to be 2y because y is positive. Okay, so that's one result there. And hopefully you can see the reason why the y remains is that when you multiply the 2 fraction bits together, you get a y squared, whereas the x's cancel and the z's cancel. So we can say similar results similarly, and I'm going to pick different pairs. So I might pick first and the third, for example. We would have xy on z plus zx on y greater than or equal to 2. Now, considering if you multiply these together, the y's would cancel, the z's would cancel, and we'd have an x squared, and when you root that, you'd get an x. So that's that result, and that's the first and the third pair. So let's consider the second and the third pair. You would have yz on x plus zx on y greater than or equal to, and if you can multiply these together, the x's would cancel, the y's would cancel, and you'd be left with a z squared, and when you root it, it'll be z. Okay, I'm not going to finish off this proof. I think you can do it from here, so I'll let you do that in your own time. But you'd do 1 plus 2 plus 3, and you'd have on the right hand side, you've got a 2x plus 2y plus 2z. You'd take out the 2, and on the left hand side, you'd have a common factor of 2 as well, and you divide that out. because we're time poor, I'm going to jump to the HSC question on page 5. So this was last year's HSC question 15A. We start off with the typical expression to say that we're allowed to assume AMGM. So using this fact, show for all non-negative real numbers that this. Okay, so we need to get that result. So I think my method of doing it was to focus. I focused on this side a bit, and I thought, well, how can I get this from an average of two things? Well, and then I realized I could set x to be a squared plus b squared on 2, and I could set y to be c. And if you average these two things out, if you add them and divide by 2, you will get this particular result here for this side. So that's what I did. So let's go. So a squared plus b squared on 2 plus c, all divided by 2, is greater than or equal to the root of the product of the top bits. So a squared plus b squared on 2 times by c. Okay, and this left-hand side is exactly precisely what we were after. A squared plus b squared plus 2c on 4. And now we need to manipulate this side. And the key thing was to note that this bit here, we can use the AMGM result again. So if you do that, it's going to be greater than or equal to the root of the product here of a squared b squared. Okay, and the root of a squared b squared is just ab. So this will be square root abc. And we've got the result as required. Okay. That was one method of doing it. There was another method of doing it, which if you want, you can have a look at the HSC solutions. They did this method, and they also did a method where they reversed and they started from the left-hand side and they bracketed the AB, and then they worked from there. So that's part I. Part II. Using part I, or otherwise, usually when they say that, use part I. Show for all negative numbers a, b, c, that, and we got that expression there. Notice, what do I notice? I notice we've got a, b, c, we've got 3 variables, so often 3 pairs is what we're after. I've also got an a, b, and a c at the back. Okay, that's interesting. We've got it on 6, not sure where that comes from yet, and I've got a root ABC, which sort of looks to come directly from there. So I think the logical thing is to look for 3 pairs, and I think let's use the previous result and just rotate A, B, and C around a bit. Okay, so so from part I, let's change it. So instead of it being a squared, let's say make it b squared, and instead of b squared, let's make it c squared, and then it'll be plus 2, and it'll be the other letter, which is a over 4 is greater than or equal to, and then once again it'll be root abc. Okay, and let's adjust again, rotate around. So let's get a squared plus c squared plus, and then it'll be 2b on 4 greater than or equal to root abc again. And let's call this now equation 1, equation 2, and equation 3, and let's add. Okay, we've got three pairs and we're adding. Okay, 3 variables, bit of symmetry involved. I think 3 pairs and adding is the way to go. So let's do that. So we get a squared plus b squared plus 2c on 4. If you want to work ahead and try and get the result by yourself, go on 4 plus a squared plus c squared plus 2b on 4. Greater than or equal to, we've got root ABC plus root ABC plus root ABC. Okay, remember not to skip lines of working out here. So that'll be 3 lots of root ABC. This one I've got, if you look at a squareds, we've got 2a squareds, we've got 2b squareds, we've got 2c squareds, and then we've got the plus 2a plus 2b and plus 2c. So what's kind of nice, we've got a common factor of 2 there. We can divide the left-hand side by 2, and we get a squared plus b squared. Hopefully you can see it popping out now. Over 2, and then we just divide by 3 to get our result. Okay. As required. And that was 4 marks in the HSC last year. Okay. we've run out of time to do the second example on page 4. Maybe we'll get back to that next week. But just quickly talking about your homework to complete for triangle inequality, Cambridge 2D, question 13, 16 to 18 on page, I think that's 79. And also do the past HSC questions for this topic, okay? See you next week.